So I made a new tab on Blackboard called References and Tables. And if you click on that, you will find at least the start of something that might be useful to you. Tables and charts, I started with the Agresti T table, the Agresti Z table. I can also add the maybe later on add the our textbook ones to that as well. Procedures, I put in the stepwise, the number of steps in hypothesis testing. That was a slide off of one of the PowerPoints. And I put in I updated and added the t-test variations, how to solve them manually. And I'm going to show you that a copy of that document in just a moment. Okay, I also added a special section here, a special item, review reference materials that I'm going to use now. Okay, and so for instance, t-test using SPSS for independent samples. Okay, that's a document that I made that goes step by step with little pictures of how to do an independent samples t-test using SPSS with data that you might be given on an exam. I also gave you three samples, one for a single sample test, one for independent samples. And whenever we say independent samples, we mean two independent samples, and one for a paired sample test. And also here's that same document with variations updated a little bit, make it a little clearer, and our T and Z table and our steps. So if you want to work along with me, you might want to download these materials, or you probably have them sitting around on your computers right now. Anyway, but at least the three data sets, and you might want to maybe open up the two instruction guides on how to use the t-test. This one is for doing it manually, and this one is for doing it using SPSS. So I'm going to get started with, I'm going to get started by opening those up. I'm going to move this out of the way. I've already downloaded them for myself. Okay, so let's take a look at what I have here. Okay, so t-test using t-test, let's see where I am here. T-test variations. Okay, I'm going to open that up. And this is a document that we used in class, updated a little bit. And basically, I went through this and kind of put a little bit more descriptive material, mostly the blue stuff that you see in here. For instance, in a single-sided test, you would state your null and alternative hypothesis. You'd start with that. Typically, that would be the mean for group 1 is equal to the mean for group 2. Of course, we would be substituting what the mean for group what group 1 is and what group 2 is. For instance, the mean for males versus the mean for females, or the means for diabetics versus non-diabetics, and so on and so forth. Then you would choose an appropriate level of confidence that you want to work with. In other words, acceptable level of error, which is your alpha error, your type 1 error, your alpha error, and that's typically 0.05. It might be different. It could be 0.01 at times. But for starters, most of the time, you're going to be working on 0.05. But keep your eye open for that. And then typically, you would have to calculate your standard error for your sample. With a single sample test like this, there's only one sample, and you can compare it to a known mean. So it's pretty simple. It's going to be the standard deviation of the sample divided by the square root of the sample size to get your standard error. You calculate a t-value. The t-value is how far the mean for your sample is from the known mean, mu, for the other population, right? That's actually a distance. Dividing that by the standard error tells you, instead of how many numerical values that they are apart, tells you how many standard errors apart they are. And we know if that t-value gets up into the 2 range, that the difference is so large that it's not going to happen very frequently if the two means for the two populations are the same. Okay, so in order to decide whether they're far enough apart, if it's a small sample, we would then calculate the number of degrees of freedom so that we could look up a t-critical on a chart on our t-table that we would need to exceed in order to reject the null hypothesis. So in the case of a single sample test, it's easy. The degrees of freedom is the sample size -1. You look up the critical value of t. For instance, if it's 10, if it's a sample size of 9, degrees of freedom are 8. The critical value of t, I think, is 2.3 something. And then we would compare the t-value that we calculated here to the critical value of t. And if we've exceeded the critical value of t, it means we're more than that number of standard errors apart, and we're sufficiently far apart that we would expect to get that big a difference between the mean of this one mean of our population for our sample population to our known mean that we're willing to take the risk and reject the null hypothesis. In other words, the p-value is less than 0.05. Okay, so I'm going to go ahead and do this. And now you'll notice that I also gave it to you here for 2 sample t-tests with equal variances, for 2 sample t-tests with unequal variances, and for paired sample tests as well, and also for paired samples, and also for actually paired samples is the same thing as a single sample t-test. I'll get to that in a second. Okay, and also for proportions if you're working with proportions. I'll come back to this after we look at this, the same activity, the same work being done in SPSS. So I'm going to start with my independent samples t-test. I'm going to open up my independent samples t-test. I'm going to open SPSS, and I'm going to, from SPSS, I could have just double clicked on the file, and if our computer is set up well, it'll recognize an SPSS file, it'll open in SPSS automatically, but just so we go through the motions, you can see what I need to do if I have to navigate to it instead. So I started up SPSS, okay, and it should give me a chance to work on it in a moment. Okay, here we go. Okay. It's a little slow. Okay, so if I can't work that, nope, still not let me do this. I'm going to try it again. Not happy for some reason. I'll give it another try. Okay. And let's see if we get a little luckier this time. Here we go. At least I think we're going. Okay, here we go. Okay, opens up with this welcome window. I'm not going to bother to use that. Opens up with a blank sheet for a data sheet for SPSS. I could actually type data in here now if I wanted to, but we already have a file, as you probably will on the test as well. I'm going to say open data, and I'm going to navigate to, happens to be on my desktop. I'm going to navigate to my folder, review session, and I'm going to open that independent samples t-test. It's called heart rate. I'm going to open that up, and the data file should open up. And here's our data file. You can see the data here. You'll notice that there's 2 columns. That means that there's 2 variables. If I click on the variable view, you'll see a description of those variables. Okay, the first variable is named heart rate. The second one is named sample for some reason. And if I go across here, you can see that heart rate is a scalar variable, but sample is a nominal variable. In other words, which of the 2 samples is this? And if I click on the value labels for sample, little box comes up. I can click on that, and it lets me know that 1 in this second for the variable samples. In other words, the second column. When you look at the data view, 1 in that column represents athletes, and 2 represents scholars. Okay, if I go back to my data view, you can see athletes and scholars. Matter of fact, I can go up here to view, and I can turn off the value labels. If I do that, you can see really it's 1 and 2. But since SPSS knows that 1 and 2 represent scholars and athletes, we can have it fill it in for us if we want. Okay, so now we have 2 samples here. One drawn from athletes in a population, a large population of athletes, maybe an entire university or a whole state university chain. We've randomly selected 6 athletes and taken their resting heart rate, and then we've randomly selected 6 scholars, and we've taken their resting heart rate. And our hypothesis, now we have to establish our null hypothesis. Our null hypothesis is that the mean heart rate, resting heart rate for athletes in the state university system is lower is different for athletes and for scholars. Okay, so I want to prove that, but I only have samples here. We're really interested in the population means, not in the sample means, but the sample means are the only thing that we have to work with. So our null hypothesis is mean heart rate for athletes is equal to mean heart rate for scholars. Our alternative hypothesis is the mean heart rate for athletes is not equal to the mean heart rate for scholars. That's a two-sided test. We're not prejudging whether scholars have a higher resting heart rate or a lower resting heart rate than athletes. A two-sided test is a more rigorous test than a single-sided test. So, but on occasion, you may bump into single-sided tests also. I'm not going to work with that right now, so that until we get through at least this. Okay, so let's take a look at this. What can I see here? Well, first of all, I can go to Analyze, Descriptive Statistics, and Explore. And I can ask it to tell me, let me move the heart rate into the dependence list and the sample into the factor list. And I can ask it to tell me the descriptive statistics for the heart rate for these two groups in the nominal variable sample. I'm going to click OK. An output window will pop up. And indeed, here we go. We get, for athletes, the mean heart rate is 63 of our sample. The mean for scholars is 70. Each one of these has a standard deviation. For instance, 5.16 for athletes and 6.5 for scholars. Okay. Now, interesting enough, one of the things we want to look at is we see that there's a difference in the mean, that athletes, not surprisingly, really have a lower resting heart rate than scholars. And I also see that the standard deviation of these two are pretty similar. You know, certainly one is not twice what the other is. So in my head, I'm saying to myself, well, maybe I can assume that the two variabilities within the two populations are the same. Okay, so if they were double one another, if this were 12 and this were 5, then I might assume that the variabilities in the two groups are different. So as a rough rule, that's the way we would approach this. It's not a hard, fast rule. It's just a judgment that you might make, which is convenient to make based on the data that's available to us. Okay, so I'm gonna move this out of the way. I'm gonna go back and look at this. And I'm gonna say to myself, okay, now my null hypothesis, my alternative hypothesis have been established. Now I want to know what level of confidence do I want to have in my result? What level of type 1 error or alpha error am I willing to accept? And typically, you might choose an alpha error rate of 5%, 0.05. So in other words, you want the two means to be so far apart that that distance, that difference in magnitude of the two means, that magnitude of that difference would only occur less than 5% of the time if the null hypothesis were true. Since it would only occur less than 5% of the time if the null hypothesis were true, you feel comfortable rejecting the null hypothesis and accepting the alternative hypothesis that the two means are really different. So now we're going to actually go ahead and test that. I'm going to say Analyze. I'm going to go down to Compare Means. And then, since this is two separate independent samples, athletes and scholars, I'm going to go into Independent Samples T-Test. In the background there, when you say independent samples, keep in mind that that really means two samples. So I'm going to click in here. A window comes up. The numerical variable goes into the test variable. That's the variable that we're calculating the mean of. The grouping variable is the groups that we're going to divide that up into. So I'm going to put the sample variable, which is the nominal variable, in other words, athletes or scholars, in there. Now notice there's two question marks in there, and it won't give me an OK box over here until I click Define Groups and let it know that the number behind this, the identification for these two groups within the sample variable, is 1 for athletes and 2 for scholars. Then now that I've let it know, you can click Continue, and you can click OK to continue with the t-test. Then click OK, and comparison means. And okay, so now we have our t-test. What comes up first is our descriptive statistics, which we just saw. Really, we saw the means, standard deviations, and so on and so forth. It feeds that back to us as part of the t-test. But we also see a calculation down here that tells us the t-values for our t-values and our significance, our probabilities for our t-test. Now notice that there's a section here. First of all, number one, notice that independent samples test. Notice that there's two lines. One line says equal variances assumed. Remember we said for this analysis we were gonna assume equal variances are assumed because of these being so close together, one not being twice what the other is. And the bottom line is equal variances not assumed. If the one was twice what the other was, we wouldn't have used the top line, we would have used the bottom line. Another way to do that is SPSS actually does a test for equality of variances. And this test is represented in these first two boxes. The result of this test is a statistic called F, and it's 0.147, but also a significance which goes with that value of F, and that is 0.709. Imagine another kind of null hypothesis. The null hypothesis is that the variances are equal. Okay, well, in that case, we're not going to reject the null hypothesis, equal variances, unless this significance is less than 0.05. You can also call this a p-value, is less than 0.05. Since it's not less than 0.05, we do not reject equal variances assumed, so we stay with the top line. Okay, had this been less than 0.05, we would have rejected equal variances assumed, and we would have used the bottom row instead. Equal variances not assumed, an alternative hypothesis, kind of. Okay, and in fact, you notice that you got same conclusions that we made off the cuff when we said, well, they're very close together, so I'm going to assume equal variances. This test also winds up assuming equal variances. So what's our t-value? Our t-value for the actual t-test, in other words, the difference in the two means divided by the standard error, the combined standard error in this case, the standard error is equal to negative 2.164 for 10 degrees of freedom. It's 10 degrees of freedom because there's 6 people in one group, 6 people in the other group. Degrees of freedom in independent samples t-test is n1 plus n2 minus 2 for two groups, right? So that would be 10 degrees of freedom. So one way you can check to see if you can reject the null hypothesis is to look up what the critical value of t is for 10 degrees of freedom. Okay, and I might as well go ahead and do that, right? Just so you know that you can keep me honest. So express these t-table for 10 degrees of freedom. The critical value of t is 2.28. I'm going to put that away. Okay, so what did we calculate our t-value to be? 2.164. So we have not exceeded the critical value of t in this case, right? So we fail to reject the null hypothesis. Well, you don't really even need to do that. You don't need to go to the t-table because SPSS also calculates the actual probability, the p-value, for getting this extreme a number with this number of degrees of freedom for our t-test. So in other words, the probability that we would get this extreme a difference between the two means, given this number of degrees of freedom, is 0.056. Right? So in other words, this would happen almost 6% of the time. Well, since we want these values, this number to be so extreme, this difference in standard errors apart of these two means to only occur less than 5% of the time. In other words, we want a p-value of less than our alpha of 0.05. Since it's not less than our alpha of 0.05, we fail to reject the null hypothesis. Same conclusion we came to here, we come to here because this is not less than 0.05. Had this been less than 0.05, we would have rejected our null hypothesis and accepted our alternative hypothesis. Okay, so I'm going to take some questions in a second, but before I do that, I just want to show you that I made up a table here on using SPSS with this example, to evaluate whether or not you can reject a null hypothesis. So you would establish your null hypothesis. In this example, mu for athletes and mu for solids. Mu for athletes is not equal mu for solids for alternative. You choose your level of confidence, 0.05. Alpha is equal to 0.05. You open your file, open data. You navigate to the data file. In this case, it's heart rate independent samples. That's SAV. You'll notice that there's two variables in that file. Here you go. You can see it on here. You notice that there's two variables in that file. Heart rate, which is numerical, and sample, which is categorical or nominal. To compare the mean heart rates of athletes and scholars, you perform an independent samples t-test. Okay, you go to Analyze, Compare Means, Independent Samples t-test, and you then can go move the numerical variable into the test variables box. You move the categorical variable into the grouping variable box, and you let SPSS know what the grouping variable numbers are or identifiers are, so it can decide on how to deal with the two groups. Well, your output window pops up. It looks something like this. And if you're interested in your t-test, you focus on the lower part of that, which is the t-value. And so if the significance is less than 0.05, greater than 0.05, use the top line. If the significance here is less than 0.05, you use the bottom line. Okay, that's where our variance is equal or unequal. And in this case, we're going to use the top line. Our t calculated is here. Here's our degrees of freedom, by the way, also. And our p-value is here. If this p-value is less than 0.05, we reject the null hypothesis. So we calculate it, t critical, number of degrees of freedom, if our t calculated is greater than t critical for that number of degrees of freedom, we reject the null hypothesis. Or if the significance two tails is less than 0.05, you reject the null hypothesis and accept the alternative hypothesis. Otherwise, you fail to reject the null hypothesis. You never accept the null hypothesis, you just fail to reject it, such as in this case. Okay, so I'm hoping that'll help you out. I'm going to try and do one of these also for the other two options, the single sample t-test. I'm going to run through that using SPSS now and paired sample t-test using SPSS now, so that you can get a look at it. I may or may not be able to get this done with all the images I got to capture and stuff like that before the test tomorrow. But you have that. That's under that tab, that reference tab that I created. Okay, so questions. Do you guys have questions on that so far? Got to be some questions, right? Are you comfortable with that? If you got it on a test, you'd be able to do it. So if the T critical was 2.3 in the last example, did it not exceed the T critical? You want your calculated T that you calculate using SPSS to exceed T critical from the chart, right? So if T critical is 2.3, your T calculated does not exceed 2.3, so you fail to reject the null hypothesis. Okay, now keep in mind that we're only talking about the absolute value. We don't care about negative and positive sign. We're just talking about the absolute value. The only reason one is negative, one's positive is because you happen to subtract mu1 from mu2 instead of mu2 from mu1, but it's really the same distance apart. That's really the key here. Does that make sense to you? That really it's the positive value. You don't have to worry about the sign. It's just the size of the number. And you want the T you calculate, this T, to exceed the critical value of T from the table in order to reject the null hypothesis. Did not quite understand. Levine portion. Okay. Okay. So the Levine's portion of this thing, this part, let me get this out of the way. Uh, this part, this is simply a statistical test to help you decide whether to assume equal variances or don't assume equal variances. So if this significance is less than 0.05, you reject the idea that the variances are equal, and you assume that they're not equal and use the bottom line instead. Notice they're almost exactly the same. The p-value is different a little bit, right? In this case, it's just a little bit different. Sometimes it'll be more different, right? But the Levine's test, these first two columns, are what you can use if you want to go beyond just kind of like a general rule, of whether it's double or not. If you want to be more accurate than that, you would use these two numbers, or especially the significance in this part, to decide whether to use the top line or the bottom line. Okay, the logic here is that you assume equal variances, kind of like what we do all the time anyway, right? We assume that things are equal to start off with until we can prove they're different. So you would assume equal variances unless the significance is less than 0.05. Well, since it's not less than 0.05, you would stick with the top line. Okay, and if it is less than 0.05, you would then get all your values from the bottom line. Okay, and I think if you look at the document, I gave you a kind of a chart there where you could kind of, let's see if I can't get it open again. I gave you kind of like a little chart here where you could take a look at this, and you could say if significance is less than, if this significance is greater than 0.05, use the top line, and it is greater than 0.05. So if it's less than 0.05, use the bottom line. And so in any case, whichever line you use, the t calculated, your calculated t value is this number right here. Your p-value that goes along with the probability of getting that extreme A value if the null hypothesis is true is here. In other words, this is what you want to compare to your alpha. If this is smaller than your alpha, that means that your likelihood of error is less than your alpha, less than 5%. If it's bigger than alpha, then your likelihood of error is greater than 5% if you reject the null hypothesis. So in other words, in this case, we failed to reject the null hypothesis. Two reasons, both of them go together. One reason, because this, for 10 degrees of freedom, the critical value was 2.28, but this is only 2.16. It's smaller. So since our t calculated is less than the critical value from the table, the means are not far enough apart for us to reject the null hypothesis. Also, because the p-value is bigger than our acceptable level of error, which is 5%, we failed to reject the null hypothesis. These will always agree with one another, by the way. Okay, does that help? Okay, good. All right, so let's move on to another version of this. Okay, so I'm going to take a look at this for paired samples. Now, paired samples, this is the situation where, let's see, independent samples. I think I got one here. Here we go. Fluoride, paired samples. I'm going to open up this database. I'm not going to go through the file open procedure. I'm just going to open it up. And I have, this is fluoride paired samples. And this is the amount of fluoride in drinking water before and after a filter is installed. Or before and after, maybe it's before and after we treat a well or something like that. I don't really know where these numbers came from, but let's say that that's what we're dealing with. So in other words, this is the same well, but it's the sample before and after we treated it. So this is another well before and after it was treated. So the idea here is that instead of comparing one group, the mean of one group given a treatment versus a completely different group given a treatment, where you could have a lot of variability other than this thing that we're looking at between the people or the subjects in that group, Instead, we're just looking at the differences before and after for each individual, say in this case, well, or person, or subject, or animal, and so on and so forth. And that's a lot more informative because then we don't have to worry about if one group had a lot more smokers than the other group, and so on and so forth. We're actually just comparing each person to themselves. So if they were smokers before and after, right? So in this case, we're really interested in the difference between these two groups, not so much the individual values here. So in this case, in order to compare the differences, we're really interested in what's the difference between before and after for each one of these. Now, we could calculate the difference. In fact, I could do that here. You just want to take a look at it. Compute variable. This variable is going to be equal to, I'm going to say after. I'm going to call the target variable difference. Is going to be equal to after minus before. Okay, and I'm going to say, okay, let's see if it works. Okay, and there you go. I created a new variable called difference, and this is the difference. Now, really what I'm interested in knowing is the average difference before and after. If there is no effect on the intervention, on what we did, if there's no difference between the values before and after, then the average difference, we would expect it to be 0. So really, this paired sample test is really just a single sample test where we find the mean difference and we compare it to the value 0. So I'm actually going to go ahead and do this. Analyze, compare means. Okay, I'm going to go over here to, so we could do it as one sample t-test, but instead I'm going to do it as what's given to us, paired samples t-test. So SPSS wants to know, well, what are the two variables, before and after variables? Well, one is after and one is before. Don't really care which one I'm putting in front. Okay, and I'm going to click OK. SPSS is then going to run our t-test for the difference between these two means. And here we go. Now, in this case, it's only a single sample, and we're comparing it to the value 0. Okay, except that I forgot something there, didn't I? Let me do that again. Analyze, compare means, paired sample t-test. I forgot to put in paired sample t-test. Okay. Okay. Oh, okay. Never mind. Paired sample t-test. Okay, it's going to compare it to difference 0 automatically. I didn't have to tell it 0. The reason why I bring that up, you'll see in a second why I hesitated there for a moment. Okay, so let's see what happens here. Well, the mean difference was 12.2. So 12.2 is pretty different than 0, but let's see if they're different enough for us to reject the null hypothesis. So let's go all the way over to here. The t-value for 12.2 minus 0 divided by the standard error is equal to 3.588. So our t-score is 3.588. Our degrees of freedom is 15. There's 16 wells or people or subjects or whatever in this sample, so it's n minus 1. It's 15. The probability of us getting this extreme a difference between the 12 and a difference of average difference of 0 is 0.003. So we would only expect to get this big a t-score less than 1% of the time. Well, we're willing to accept rejecting the null hypothesis as long as there's less than a 5% chance of getting a difference as large as what we observed here. So since our significance is less than 0.05, our p-value is less than 0.05, in this case, we reject the null hypothesis and we accept the alternative hypothesis. Now notice that degrees of freedom is 15. My guess is that the t-critical for that value, for 15 degrees of freedom, probably around 2.1. Well, 3.5 is way bigger than 2.1, so our calculated t is bigger than the critical value of t from the table. So that's the same thing as getting a value less than 0.05. So this is evidence to reject, and this is evidence to reject. Okay, more questions. Should we be prepared to manipulate data in SPSS for exam? Well, that's a good question. I think probably you'll want to be able to do at least some of this, if you're given data sets and so on and so forth. You might be given data sets and asked to do a t-test like this, or you might be given the data set as an Excel file. You might be given it as an SPSS file. You might be given it as both. So you want to be prepared for that. You also might possibly be given the table, the output table, and asked to interpret the output table. Where did the zero come from that you mentioned? Well, the zero comes from, see these differences, right? The average difference here between before and after, the average difference is 12. Now, if there had been no difference between before and after for the whole population, then we would have expected our average difference to be zero. Half the time we get a difference, a positive difference. Half the time we get a negative difference, but we'd expect them to cancel out and the average difference to be zero. So what we're doing is we're taking the mean difference, turns out to be 12. X bar happens to be 12. And we're comparing it to what we would have expected if the null hypothesis were true. No difference between before and after, which would have been zero. That's where the zero comes in. And in our output table, you can see there's the mean difference. And really what you're doing here is you're saying, calculating t is equal to x bar minus mu difference, which is the difference, the mean difference if the null hypothesis is true is zero. So in other words, 12 minus 0, or 12 divided by the standard error 3. So 12 divided by 3.4 is a little bit less than 4. And in fact, here it is, 3.588 is where that actually came from. And the degrees of freedom are 15 because the sample size is 16. There's 16 pairs. And the probability of getting 12 for the average of those from that sample, if the real mean difference is 0, probability of that happening is less than 1%. It's 0.003. And that's really where the zero came. In fact, watch this. I'm glad you brought that up because I have another data file over here, which is a single sample t-test. I'm going to go into that. I'm going to say analyze. Whoops, I'm going to say open data. And I'm going to navigate to it. Our single sample t-test. I'm going to say open. Okay, here's a single sample t-test. Our single sample t-test is its particulate levels, particulate matter in micrograms per cubic meter. Okay, and the variable name is particulate. It's a numerical variable, scalar variable. And I'm going to go over here to our data view, and here are the numbers. And this is for a particular city, let's say. Let's say we took 10 samples around New York City, 16 samples randomly around New York City. We didn't have the, but in and we know that the average particulate levels for Los Angeles are equal to 40. But we don't know what it is for New York, but we know the mean for Los Angeles because they have continuously sampled the air or something like that. We know the true mean for Los Angeles is 40. In this case, we don't know what the true mean is. All we know is the 16 locations that we sampled. So in one case, we have a sample. In the other case, we have a known mean. So the null hypothesis here would be mu particulate levels for New York is equal to mu particulate levels for Los Angeles. Now we know mu for Los Angeles is equal to 40. So we can say instead our null hypothesis is mu particulate levels for New York is equal to 40. And our alternative hypothesis is mu particulate levels for New York is not equal to 40. In other words, not equal to the known mean for Los Angeles. Okay, so we could use that. Now I'm going to use alpha is equal to 0.05 again. And then I'm going to go ahead and I'm going to analyze this and compare this results of this single sample to a known value. I'm going to say analyze. I'm going to say compare means. So this time I'm going to say one sample t-test. Because one mean is known, the other one has to be done. It has to be calculated from a sample. I'm going to go here to one sample t-test, particulate matter, that's the one we want. I'm going to move it over. Now I'm going to put the test value in here. What am I comparing it to? Well, I'm comparing it to the value that I know is true for the mean of all of Los Angeles, which is equal to 40. Obviously, I don't really know that, but let's make believe we do, right? That's equal to 40. And then I'm going to click OK. What's going to happen is we're going to do a t-test. And the t-test is going to compare the mean value x bar for our sample minus 40, mu1 minus mu2, x bar minus mu 40, over the standard error and give us a t-value. And based on the degrees of freedom, which is going to be 15, because it's going to be a single sample with n equals 15, okay, based on the degrees of freedom, it's going to calculate a t-value for us, and it's going to calculate a p-value, a two-tailed significance. So I'm going to click OK. We're going to get our output window come back up again. Let's read it. Let's go down here to, let me bring it up. Oops. It got away from me there. Let me bring this up to the middle of the page. Okay, let's read our one sample t-test. Well, the t-value came out to be 1.529, 15 degrees of freedom, and our significance is 0.147. And what do we do when we get a significance of 0.147? Do we reject the null hypothesis, or do we fail to reject the null hypothesis? I'll wait for somebody to... We failed to reject it. Exactly. This has to be less than 0.05. In other words, the probability of getting this big a difference, this t-score, this big a t-score difference, this number of standard errors apart between the two means, we want that to only happen less than 5% of the time if the null hypothesis is true. So if that's only going to happen less than 5% of the time, we're willing to take the risk and say that we'd only get this extreme a difference, this extreme a t-score, less than 5% of the time. If the null hypothesis is true, the two means are equal. Well, then if this is not less than 0.05, we're not willing. If we're not willing to accept 14 or 15% chance of being wrong, rejecting the null hypothesis. But if this was less than 0.05, we would reject it. In this case, we fail to reject it. Okay. Again, if you want to be a little bit more geeky about this, you'll notice that the t-score is very small. If you went over and looked up the t-value, you would t-critical for 15 degrees of freedom. My guess is it's probably 2.05 or something like that. And this is well less than 2.05. Remember, we were talking about the magnitude. Don't worry about the sign. This is well under 2.05. So we wouldn't expect the significance to be less than 0.05 either. Right, so we failed to reject the null hypothesis. The reason why I was starting to talk about, hang on, I'm going to go back here again, analyze, compare means, paired sample t-test. Notice, nope, I didn't mean that. Analyze, compare means, one sample t-test. Notice that when we open this up, what value was filled in here by default? It was 0. So basically, this was getting ready to do a two-paired sample t-test as if we were just looking at the comparison to 0, a difference of 0. That difference, when we're doing the paired samples, right, we're looking to see whether the differences between before and after, or measurement A and measurement B for each person, whether those measurements before and after are the same. If they're the same, then the difference is 0. And if the average difference is 0, if the average difference is 0, then the null hypothesis is true, that there's no difference there's no difference between the average difference and the value 0, which means that we can't reject the null hypothesis and say that there's a difference between before and after, right? So in this case, if we were doing that, when we do the paired samples, it's just doing exactly the same thing, except it doesn't bother to ask you for the test value. Like here, we had to tell it that the particular levels for Los Angeles are 40. I'm going to change it to 50 now. Particular levels are 40 because it automatically assumes that since you're doing paired sample t-test, you're looking to compare it to an average difference of 0. So no need for it to ask you for that value. But here, since it's you're comparing it to something that is a value other than 0, you have to actually tell it. Watch what happens when I do 50 instead, when I compare it to the value 50. When I compare it to the value 50, wow, look at the size of that t-value, and look at the significance. See, we have a big enough difference now when we compared it to 50 that we would reject the null hypothesis because this is less than 0.05. Okay, so okay, good. So now, just so you know how to do it, I want to, in case it comes up during the test, I have a file here, which is an Excel file, heart rate. It's the same file we had before. It's the heart rate Excel file. I'm going to double click on that and see what it looks like. If it ever opens up Excel, there it goes. Okay, let's give it a moment. Okay, so if you look at this, this is the same data we were just looking at. This is the number 1 represents athletes, number 2 represents scholars. These are the heart rates. I think they're the same numbers. I don't think I changed them. I think they're the same numbers. The only problem is that it's very nice I have this Excel file, but what if I want to import this Excel file into SPSS because it's going to be easier to do the paired samples, the independent samples t-test. Independent samples because you got this group and this group, 2 different groups. So I'm going to say save as, and I'm going to put this on our desktop, on my desktop. Save, and then I'm going to close this in Excel. SPSS doesn't like working with files that are open in another program. It may not let you do this if it's still open. It'll give you a warning, most likely, that it's open in another program. So I want to import that Excel file into SPSS. So I'm going to go up here to File, Open. Don't bother with import. Just say Open, Data, and then go over to your desktop or my desktop. And I don't see it there. And the reason why I don't see it is you're only looking for .sav files, SPSS files. So I have to tell it, well, you know, there's also Excel files here that I want to work with. So I could just click on that, or I could even just click on all files. So everything appears there. But I'm going to just so it doesn't get confusing, I'm just going to pick Excel files. Okay, so now you'll notice that my Excel file, heart rate, Excel file.xlsx. That's my Excel file. So I'm going to click on that and say open. Okay, notice I wouldn't have seen that if I didn't switch over to show me Excel files on this folder. I'm going to say open, and it's going to open the window, and it's going to give me a little bit of information. It's going to tell me that this worksheet has data between A1 and B13. Well, that sounds like where my data is. It's in 2 columns, right? So it sounds right. In fact, here it is. It's showing it to me. It's giving me a little preview. It's also telling me that it's reading the variable name from the first row of data. Okay, that's important to know whether or not that's correct, because notice that in our Excel file, the first row was not the values in our Excel file. The first row said heart rate and sample, right? So we wanted to understand that that's true, that the first row has the variable names. That way, if I unclick that, it's going to think that that is data. See, it looks like that heart rate and that sample is part of the data file, and we don't want that. We want it to know that those are the variable names, not part of the data itself. So I go ahead and click that. In cases where you don't have that, right, where you don't have the variable name in the top row, and you have data there, you want that unclicked. Otherwise, it'll put the 65 and the 1. If the heart rate sample were not there, it would put 65 and 1 up into the variable names, right? If we told it that that the first row had variable names, right, and it didn't have variable names, right? So in this case, we want it checked off. Okay, so I'm going to click OK, and it's going to open this file in SPSS. The only downside to this is that notice that if I go up to the value labels, look, it doesn't know that 1 and 2 represent athletes and scholars. I can live with that. If you're just going to calculate the numbers, you go to Analyze, you can go to Compare Means, in this case, Independent Samples. Okay, you can put that in there, and you put sample in here. Whoops. And you can tell it the 1 and 2. And the result you get, okay, the result you get when you have your output table is that notice over here it says sample heart rate, sample 1, group 1 and group 2, instead of, if I can go back and find it, instead of before and after, or instead of athletes and scholars, it says 1 and 2, right? If you want to code that, you can. You can go into the variable view, and you can make sure it says that that's nominal, got it right, and that the first variable heart rate is scalar, right? But then you can go into the value labels, and you can say 1 represents athletes, and 2 represents scholars. And now it'll recognize that when you make a table, when you look at your data file, it will actually recognize that. Okay, so now the data is imported into SPSS, and you can work with it here instead. You can do that for single sample t-tests, for paired samples, and so on and so forth. Although paired samples, it wants the data before and after in 2 columns, before and after, just as you saw it before. So the other way that you might be, now let's go back to that description of the files, of these other files. Where are they? Okay, SPSS, t-test variations. Okay, so now in the calculations here, for a single sample t-test. Now, I went over this. If you look in the review session, I think I went over this in the lab. I posted the lab video from this past Monday, and also in the review session I just did on Thursday. Both of those are available on Blackboard. I think one's in the announcements and the other's in the session for last Monday right now. Okay, so you might have to scroll down to the bottom of the stuff in the folder for that session. Okay, so I actually went through these examples, but I kind of I made this a little bit more definitive so that you could see what calculations you had to do in order to actually do this. You could do this manually, calculate the mean, the standard deviation, then calculate the standard error from the standard deviation, and we describe the sample size, and then calculate the t-value, x bar, your sample mean, minus mu, your known value, whatever that, in this case, perhaps 99, okay, and divided by the standard error, and then you could calculate, you can compare that to your critical value based on what your degrees of freedom are. This is how calculate degrees of freedom. Now, if you have paired samples, remember when you, if you have independent samples, in other words, a 2-sample t-test, you remember from SPSS that you could have 2 situations there. One where the standard deviations are assumed to be equal, and one where the standard deviations are assumed to be unequal. Well, in the case where you're assuming the standard deviations to be equal, in other words, where the standard deviation for sample 1 is not double the standard deviation for sample 2, or vice versa, right? Well, then you would use these formulas. Okay, again, you calculate, you state your null and alternative hypothesis, state your level of confidence, alpha is equal to 0.05, and then you would count, since you think they're equal, in that case, you calculate a pooled standard deviation. This is a little tedious, but all you have to do is put in the sample size 1 minus 1 times the standard deviation for sample 1 squared, plus same thing for sample 2, and add those 2 together, then divide by the sum of the 2 sample sizes minus 2, and then divide that into the denominator into the numerator, and then take the square root of the whole thing, and that gives you a value called the pooled standard deviation. That's actually going to be, if it's not between standard deviation 1 and standard deviation 2, something's wrong, because it's giving you basically the weighted average of these 2 standard deviations. So that should be between standard deviation 1 and standard deviation 2. How do you calculate that? You can use Excel or a calculator to do that, right? So you got a pooled standard deviation. Well, then you calculate your t-value. And your t-value is the difference between the two means, in this case mu1 minus mu2, or since we don't know what they are, x1, x bar 1 minus x bar 2, divided by the standard error. When you're working with pooled standard deviation, the bottom of this equation, the standard error, is the pooled standard deviation times the square root of 1 over n over 1 plus 1 over n2. 1 over n1 plus 1 over n2. So if this is 1/9 plus 1/9, this is 2/9, and you have to, it's a little tedious. You might want to change them into decimal values to make them easier to add together, and then take the square root of it, and then multiply by this pooled standard deviation, and then divide that into the difference between the two means. I know tedious, but not impossible, right? I mean, if you're careful, if you're careful about handling these numbers. Well, degrees of freedom. In the case of equal variances assumed, the degrees of freedom are equal to n1 plus n2 minus 2. From there, you can look up the critical value of t for that number of degrees of freedom, whatever that happens to come out to be, let's say 2.1. Then you compare the t-value calculated to the critical value of t. And if your calculated t-value is greater than the critical value of t, in other words, the two means are further apart than that number of standard errors, you reject the null hypothesis and accept the alternative hypothesis. Okay, well, what if they're unequal variances? If one standard deviation is more than double the other standard deviation? Well, here you got instructions here to what to do if they're not assumed to be equal. Well, in that case, okay, we go through the same thing with the means, with the null and alternative hypothesis, and the choosing our alpha, right? And then what we do is we can calculate our t-value directly by using this formula. X bar 1, the mean for sample 1 minus the mean for sample 2, divided by the standard error. In this case, the standard error is the square root of S1, standard deviation of group 1 squared over the sample size of group 1 squared, plus the standard deviation of group 2 squared over the sample size of group 2, right? And then you can convert these into a fraction, add them together, take square root, and then divide that into the difference. That will give you your calculated t-value. So now, how do you know if you exceeded your critical value of t? Well, you need to know your degrees of freedom, so you can go to the t-table to look up what your critical value of t is for your sample sizes, for your degrees of freedom. Well, problem is that when you're assuming equal, when you're not assuming equal variances, it's a very convoluted calculation for the degrees of freedom. If you are a glutton for punishment, you can do this. But if you don't, on an exam in a hurry, most of the time, what you can do is just simply take the smaller sample and subtract 1 and use that for the degrees of freedom to look up your critical value of t. If your t-value exceeds that critical value of t, you reject your null hypothesis again. Okay, so now, finally, we get to proportions. Okay, so let me finish this up, and I'll look at the questions in a second. So now we're dealing with proportions. State your null and alternative hypothesis. Well, typically we'll be saying that proportion for population 1A for population A or group A is equal to proportion for population 2. Alternative proportion for population A is not equal to proportion for population 2. Okay, so we identify the populations for P1 and 2. Okay, but sometimes we're comparing a P to a known value. Okay, so for instance, I might ask you that, I might tell you that the proportion that 600 people out of 1,000 like chocolate ice cream, right? And I might ask you, what is, to evaluate whether you can say with a sufficient degree of confidence, in other words, alpha is equal to 0.05, whether you can say that the majority of all people in that population like chocolate ice cream, right? So the majority implies 50%. So really, what you're testing in a situation like that, it's kind of a single sample t-test. You're calculating your null hypothesis is that the proportion from your sample, P cap from your sample, is equal to 50, or P proportion of the total population, P is equal to 50%, or it's not equal to 50%, right? Have you exceeded 50%? Have you not exceeded 50%? Well, you can figure that, you can actually calculate a confidence interval for that. So you can calculate a confidence interval using, you can go back over the material in class using P, the 95% confidence interval. It's represented by P cap plus or minus 1.96. We use 1.96 all the time with proportions because our sample size is always at least 30 and 15 in each outcome. Right? So we're going to use 1.96 P cap plus or minus 1.96 times the standard error. And the standard error is calculated when we're dealing with a single sample, single proportion. It's calculated as the square root of P cap times 1 minus P cap over the sample size. We would resolve the inside of that square root, and then we would take that square root, and that would be our standard error. So P cap plus or minus standard error of 1.96 times that calculated standard error, and we would get a 95% confidence interval for that single proportion, for that population. And then we would look to see if 50% were within that confidence interval or above or below that confidence, in other words, outside of that confidence interval, in order to reject that, in order to accept or reject that null hypothesis. Now, what if you got two proportions? We want to know if the proportion of people who have diabetes in Idaho is different than the proportion of people who have diabetes in New York. We randomly sample 1,000 people in Idaho. We randomly sample 1,000 people in New York. And now we have two samples, two proportions, P cap 1, P cap 2. Well, now how do we determine whether or not we can reject the null hypothesis? Okay, so what we're going to do in that case, we're going to compare the two samples. So what we're going to do in that case is that we're going to calculate a pooled proportion, which is going to be pooled proportion P cap is going to be P cap 1 times N1 plus P cap 2 times N2 over the sum of the sample sizes. That's going to be our pooled proportion. And then we're going to calculate a z-score, which is equal to P cap 1 minus P cap 2 over, over the square root of P cap, the one we just calculated, pooled proportion, times 1 minus P cap, that pooled proportion, times 1 over N1 plus 1 over N2. We're going to calculate that z-score. And if that z-score is bigger than 1.96, that's going to be our critical value for 5%. Bigger than 1.96, we reject our null hypothesis that P1 is equal to P2. So I don't think it's likely you're going to get that on the exam, but you might get a situation where you get a single sample and you'll be asked to compare it to a given percentage, like 50% or 35% or something like that. So it's more like a single sample rather than two separate samples in this proportion. And anyway, you have this chart. I kind of updated this chart to make it a little bit more intuitive. So hopefully that if you need it, that'll help you out a little bit. So let's take a look at the questions here. Can you give an example how a problem would be worded where you would have to pool? Well, if you have, first of all, number one, you would only pool if you have two samples, right? Otherwise, if it's a single sample, there's nothing to pool. You just have a single sample. It's only going to happen when you have the two samples. So you would pool, you would calculate the standard deviation, pooled standard deviation, as we described here, in the situation where the standard deviation of sample 1 is more than twice the standard deviation of sample 2. In other words, there's a big difference between the two standard deviations of the two samples. In other words, that there's the variability in one of those groups is much different than the variability in the other group. If it's not twice that, if it's less than twice, one is less than twice the other. In other words, they're within twice, less than twice, one's less than twice the other. Then you would just assume equal variances. If they are one is more than twice, one standard deviation is more than twice the standard deviation of the other group, then you assume unequal variances. The best way to avoid worrying about it too much is to use SPSS and look at that little significance by the Levines test to decide whether to use the top row or the bottom row. Between me and you, usually the difference is so small that it probably won't make a difference which one you use, because the t-value and the significance probably will be within the level of variability that the question will accept, I would think, most of the time. Just like you saw, it wasn't much of a difference now, but occasionally it could be a difference. So, but you could use that, just you can see it in the background there. You could use that to determine that. So you can use SPSS to like really help you out with this stuff. I'm still a bit unclear on what to use to prove. Okay, yeah, I think we covered that. Can you give an example? Yeah, well, the wording's going to be all over the place. It's going to be a word problem. But you need to key in on whether or not, how many samples there actually are. Are you sampling two groups? Is there group A and a group B? Or is it a single group and you're comparing it to a known value? And then what the variabilities look like. And by looking at the data file, probably that'll help you out quite a bit in terms of understanding how to proceed. In other words, is there, you saw that there was, when we doing independent samples, we had we were looking at two columns in our variable list. We were looking at a numerical variable, which was going to calculate means of, but also a nominal variable, which had two groups, athletes and scholars. Right. On the other hand, if you're working with a single sample t-test, you're only going to be concerned about one column. And if you're looking at paired sample t-test, you're going to see side-by-side columns where each horizontal line represents an individual subject or person and is two measurements for the same subject or person, kind of a before and after, right, for the same person. So there, you're really interested in the difference before or after. What kind of difference did you get? Or was there a difference or was no difference based on the intervention, the drug or the placebo that they took, the drug that they took, for instance? So I think that's probably the best way to look at that. Yeah, you can use SPSS for any of this stuff, most likely. But you might want to practice importing an Excel file into SPSS if you haven't tried it before. You have an example of it here, and got the files I use are all on Blackboard right now under that reference tab. As long as it is not twice the difference, then we wouldn't use it. If it's not twice the difference, you use a pooled standard deviation. It's the opposite. Get it? In other words, you pool the standard deviations when the two variances, the two variabilities, the standard deviations are close. If they are twice as two or more times different, right? If one is more than double the other, you don't use a pool. You assume unequal variances and you don't pool them. If they're less than two, if one is less than double, is not double the other, like one is 5 and one is 6, then you would pool the standard deviation. If you look at that page, if you read that page, it'll, that page, like the 2 pages for pooled and for equal variances and unequal variances. I think it'll help you out a little bit as you go through it. So if, for instance, if the standard deviation of group A is 5 and of group B is 6, you assume equal variances and you calculate a pooled standard deviation. If the standard deviation of group 1 is 5 and the standard deviation of group 2 is 15, then you don't assume equal variances. You assume unequal variances, and you use the formulas that are used in that other page for unequal variances. You don't calculate a pooled standard deviation. Does that make sense? I think that makes sense, right? Okay. So I'm going to try and get some more instructions put together for SPSS for like kind of like this with the pictures for a single sample t-test and for a paired sample t-test in case that might wind up helping you out tomorrow. So I'll see if we can't get one or both of those posted by sometime tonight. Oh, good. Well, you got all this data. You can actually just do the ones that I just did right now. The one with the blue. Yeah, I hope it does. You let me know after the test. Let me know if it helped out. Okay, and we'll see. We'll see if you see any errors, you see you see a way that I could phrase it more clearly. Go ahead and suggest that to me. Pooled is only for paired. Oh no, pooled is only for pooled is excuse me. Pooled standard deviation is for two sample t-tests where the standard deviation of the two samples are close together, so you can combine the numbers to get a single standard deviation for both populations. It helps you out in the calculation. When you're doing paired samples, that's really a single sample t-test. So there's nothing to pool because when you do a paired samples t-test, you're comparing before and after, so you ignore the numbers themselves, before and after numbers themselves, and you only look at the column with the differences and compare the average difference to zero. So there's nothing to pool because you're only working with a single column or a single sample, and you're comparing it to the value zero in your null hypothesis. Okay, okay, guys. So I'm losing my voice at this stage. So good luck on the test. And like I said, if you have more questions, post them on. I didn't get a chance to look before I started here on to see if there were since this morning if there were other questions on the discussions forum. But I will check them later on tonight. I'll check in the morning. So if you have more questions, post on the discussions forum so that we can all share this, so that people that have not seen this will or rather than me answering one person's question and they're the only ones that see the answer, that a lot of you will have the same kind of questions. So perhaps we can all enjoy the benefits of sharing this knowledge together by if we work with the discussions forum rather than sticking with the emails and stuff like that. So good luck on the test. I'll see you tomorrow night. And in the meantime, if you got questions, please post them there and I'll take a look at them. Take care, guys. Good night.